Have you ever just looked at the world around you and wondered, how do we know what anything is actually made of? You know, the food we eat, the air we breathe, even the signals firing in our own brains. It's like chemists have this secret code that unlocks the deepest mysteries of matter. Well, today, we are going to crack that code together.
Okay, so let's just dive right in with what looks like a simple question. See this single drop of water? How many tiny little H2O molecules do you think are actually in there? 1,000? Maybe 1,000,000? What if I told you it was more than all the grains of sand on all the beaches in the entire world? It sounds absolutely impossible to figure out, but it's a puzzle that chemists solved a long time ago. And by the end of this, you'll know exactly how they did it.
To even start to answer that question, we first need to learn the language chemists speak. You can think of it like getting the blueprints for matter itself. Once we can read the plans, then we can start to build. And more importantly for us, to count. So first up is the most basic piece of this language, the molecular formula. The easiest way to think about it is like a parts list for a molecule. It tells you exactly which atoms you need and how many of each. That little number, the subscript, that's the key. So for acetic acid, that's the stuff that makes vinegar sour, the formula C2H4O2 tells us that every single molecule has 2 carbon atoms, 4 hydrogen atoms, and 2 oxygen atoms. Pretty straightforward, right?
But you know, just having a parts list isn't the whole story. You also need the assembly instructions, and that's where the structural formula comes in. It doesn't just show what atoms are there, it shows you exactly how they're all wired together. And this is so important, because that structure, well, it changes absolutely everything.
Now check this out, because this is where things get really interesting. On the left, you've got acetic acid, vinegar. On the right, methyl formate, an industrial solvent. Now look at their molecular formulas. They are identical, C2H4O2. The exact same parts list. But because those parts are put together in a different way, one is something you put on a salad and the other is used in insecticides. You would not want to get those two mixed up. These are called isomers, and they're the reason that an almost infinite number of different things can be built from the same basic set of elements.
And here's a super quick but really crucial detail in our new language. H2 and 2H, they might look almost the same, but they mean completely different things. H2 with that little subscript 2 means 2 hydrogen atoms are chemically bonded together. They're a team, 1 hydrogen molecule. But 2H, with the 2 out front as a coefficient, just means you have 2 separate individual hydrogen atoms floating around, not connected at all. It's a tiny difference on the page, but a huge difference in the real world.
All right, so now that we've got some of the basic language down, let's circle back to our main problem. How do you count things that are impossibly small and come in unbelievable numbers? Let's talk about the problem of scale.
So how many molecules were in that drop of water? Turns out it's about 1 sextillion. That's a 1 with 21 zeros after it. I mean, it's a number so massive our brains can't really even picture it. If you tried to give every single person on Earth an equal share of those molecules, each person would still get over 100 billion of them. It's just a lot.
Which brings us right to the heart of the matter. How do you do it? You can't just put a sextillion molecules under a microscope and count them one by one. It's physically impossible. So, how did chemists solve this? Well, they got clever. They basically invented a new way to count. They came up with this brilliant concept called the mole. And no, not the fuzzy little animal that digs up your yard. In chemistry, a mole is just a word that means a specific amount. It's just like how the word dozen always means 12, or a pair always means 2. A mole is just the chemist's word for a much bigger number. It's basically the chemist's dozen.
And what is that number? It's called Avogadro's number, and it is gigantic. 6.022 times 10 to the 23rd power. That's 602 sextillion, 200 quintillion. It's just mind-boggling. But here's the cool part. Whether you have a mole of carbon atoms, a mole of water molecules, or a mole of basketballs, you always have this exact, colossal number of them.
So why this crazy huge number? What's the point? Well, that number, the mole, is the crucial link. It's the bridge that connects the invisible world of atoms and molecules to the world that we can actually see and touch and, most importantly, weigh in a lab. And here's the key idea that makes that bridge work. A mole of carbon atoms and a mole of lead atoms have the exact same number of individual atoms, that crazy 6.022 times 10 to the 23rd number. But think about it. A single lead atom is way heavier than a single carbon atom.
So it just makes sense that a whole pile of lead atoms is going to weigh a lot more than the same number of carbon atoms.
And this table just lays it out perfectly. Look at the weights. 1 mole of carbon weighs just 12 grams, but 1 mole of lead, that's a hefty 207 grams. You've got the exact same number of atoms in each pile, but wildly different masses. This number, the mass of 1 mole, is called the molar mass, and it's the secret code on the periodic table that lets us do all our counting.
So let's put it all together. Let's see how this works. Imagine we have exactly 5 grams of copper wire, something you can easily weigh on a scale. First, we look up the molar mass of copper, which is about 63.5 grams per mole. We use that to turn our 5 grams into moles. Then, we take that number of moles and multiply it by Avogadro's number. And just like that, boom! We find out that in our little piece of wire, there are over 47 sectillion copper atoms. We just used a scale to count the uncountable.
Okay, so this is all really clever. But why does any of it matter outside of a chemistry lab? Well, it turns out this secret code, this ability to count atoms, is absolutely fundamental to our modern world, from medicine to technology and beyond.
Every single time a doctor figures out the right dose of a medicine, they're using these principles to give you the exact number of molecules you need. Scientists are using it to build tiny nanoparticles that act like microscopic delivery trucks, carrying drugs right to cancer cells. And, incredibly, it even lets us measure the chemical signals that are literally controlling our thoughts and emotions.
I mean, just take this for example. Dopamine is one of the most important chemicals in our brain. Using really advanced techniques that are all based on these same principles, scientists have actually been able to count the number of dopamine molecules released by a single neuron, and they found that one tiny little packet contains, on average, about 30,000 dopamine molecules. We've gone from counting atoms in a wire to counting the molecules of thought itself. It's incredible.
And here's the real payoff. By being able to precisely count these molecules, researchers can finally understand what's going wrong in diseases like Parkinson's or schizophrenia, where these chemical systems get out of balance. This knowledge is the absolute key to developing better, more effective treatments. It all comes back to being able to count.
So we started this journey with a simple drop of water, and we ended up inside the human brain. We've learned the secret language chemists use to describe our world, and the clever trick they use to count its tiniest, most fundamental parts, which really just leaves us with one final thought. Now that we can read and count the very building blocks of reality, what amazing conversations are we going to have with the universe next?